He is currently teaching an online class, if this is up to date, with over 13,000 enrolled students. So there's 40,000. We have to hear about that.
I'm one of them.
Okay. All right. I got to hear more about that.
You're one of them, but you're special.
All right. Dr. Impey is a past vice president of the American Astronomical Society. It's the AAS, that's the professional Society of Astronomers. He has been an NSF Distinguished Teaching Scholar and the Carnegie Council's Arizona Professor of the Year. He has written over 40 popular articles on cosmology and astrobiology, 2 introductory textbooks, a novel, and 5 popular science books. His latest book is Dreams of Other Worlds, published in 2013, and he's here to talk about that book and anything else that he wants to talk about. Please join me in giving a warm welcome to Dr. Impey.
Thanks very much, Dean and Alexander, for the invitation. Can we maybe kill the lights? So I'm delighted to be here and share some exciting research really on astrobiology, or the search for life in the universe, that's taken place in the last few years. And I'm going to broaden it to give some of the big picture of this subject. I work in observational cosmology, so some of what I'm talking about is not my research field, but I have colleagues and I'm sort of an honorary astrobiologist. It's one of the most exciting fields in all of science, moving very rapidly, as you'll see. So I've been interested enough in life in the universe to write a couple of books about it. It's always the best way to learn about something, to write a book. But my research is really cosmology, so I've written a couple of books about the universe, how it began and how it ends. And maybe eventually I'll write a book about the sloppy middle part that we're in at the moment, basically. And then Dreams of Other Worlds was fun because it's the first time I've written a science book with another author, except a textbook. Holly Henry works here, or in the area, at CSU San Bernardino, as an English professor, and that was fun to write a book with someone from another discipline. And this book was actually supported and commissioned, if you like, by NASA's History Division, because most of the missions involved are NASA missions. And then in 2013, I got kind of, not bored, but I sort of wanted to venture out of the box a little, so I wrote a novel, and then I wrote a book about teaching cosmology to Tibetan monks called Humble Before the Void, but that's another story. So let me frame the issue that I'm going to talk about today. This is a rather austere quote from a famous philosopher that many people have not heard of. Everyone knows Plato, Pythagoras, and Aristotle. Anaxagoras had strikingly modern ideas about the universe 2,500 years ago. And for him, the only meaningful or plausible thing to do with his life was to understand how nature worked. The opportunity to understand the universe is the reason it's better to be born than not to exist. I don't know if this person was able to sort of chill at a cocktail party and talk about lighter things, but it seems like he was probably pretty intense. But let's get into the mood for this, Dreams of Other Worlds, by looking at the sky that I work with in Arizona. It's inevitable. We look at the sky and know there are all those stars there, and now we know, surrounded by planets, to wonder how much is out there and what's on those other worlds. And I think we're in a very exciting time in the history of science where we may learn the answer to that question. And I can't answer that question as we speak. We still know of only life on one planet, this one. But I'm going to sort of set the stage, set the table, if you like, for what we hope to learn in the next decade. And in the history of ideas, what we're talking about is another step in the Copernican revolution. 500 years ago, it was a jolting realization that humans are not the center of the universe. The reason it was called a revolution, a word we use for social and political upheaval, was that it was disturbing to many people. It upset the power structures of the day to think that the Earth was just a planet, just a rock in space like the Moon or Mars. And since then, it's gone in the same direction. In the last century, we've learned that we're a small, relatively unimportant sector of the Milky Way galaxy composed of billions of stars, and that there are billions of galaxies like the Milky Way. And we may be on the cusp of another step in this revolution, which of course displaces us in centrality in the universe, with the recognition that the biology of this planet is not unique either in the universe. And in cosmology, an idea that I'm going to finish with, the idea that the totality of space and time visible with our big telescopes may not be all there is as well. So I'll frame my talk by asking a very simple question. And a question that was unanswerable just even a decade ago, and now is answerable. How many habitable worlds are there? By which I mean rocky planets, more or less like this one, on which all the ingredients for life exist. Whether or not those ingredients have turned into biology is the question that remains ahead of us. Let's start with our backyard, the part we might know the best because it's close. It's the solar system. People have speculated about life and habitability, of course, for centuries, and in fact, since Anaxagoras' time, for thousands of years. And in the 1930s and 1940s, in the lurid fiction of Edgar Rice Burroughs, the John Carter series, we imagined that Mars was inhabited by races of people and creatures, and it's a frolicking good time being had on Mars if we could only get there and witness it and experience this. The reality of Mars by spacecrafts in the 1970s was a little more mundane, but still intriguing. These pictures, the lower right of which was taken over 40 years ago, show clear indications of liquid running on Mars. Mars is an arid desert now. If you put a glass of water on the surface, as we speak, it would just boil and evaporate in a second. There can be no liquid water on the surface of Mars, but Mars shows signs of having been wet in the past and having perhaps had shallow seas, maybe 3 billion years ago. And due to some runaway set of geological and atmospheric conditions, the planet dried out and became very cold. We even see signs that the water can erupt onto the surface. This pair of images from an orbiter in the last decade shows the appearance of runoff down the rocky escarpment. And the modeling of this suggests that 200 or 300 swimming pools of water erupted from a subsurface aquifer and ran down this hillside, leaving this channel. So even though Mars cannot have water on the surface, it's tantalizingly close. We can almost taste it. And of course, where there's water, there could be life. So even though Mars is not inhabitable on its surface, it could host microbial life right now. And of course, the space missions and rovers that are there are trying very hard to look for fossilized evidence of previous life. But Mars is not the only place of interest in the solar system. There's a world that was first seen in detail also about 40 years ago, Europa, and you're seeing a piece of it here. The smallest features maybe the size of a football field. This is an icy crust, just an ice field, that overlays a liquid water ocean perhaps tens of miles deep. So this is a water world, not like the Earth with water over 3/4 of the surface. 100% of Europa, the moon of Jupiter, is covered with water underneath an ice pack. And once again, there's enough energy coming from the core of this moon to heat the water to perhaps a tepid temperature that we could imagine life existing there too. This is a model, a cross-section of what we think Europa looks like. NASA has just had approved a mission, the Europa Clipper, to look at Europa more closely. It's going to take a decade to get there, but that mission may well give hints of whether Europa could host life. It will not land on the moon, it'll do this all by remote sensing. There is a mission that's more ambitious, but unfunded, because NASA has its own budgetary problems, to actually land on the ice pack. used the nuclear plant in the spacecraft to melt through the ice and release a hydrobot that would explore the ocean and look for life directly. So that's what people really want to do, but it's unfunded. And then there's a world a little further away, a billion miles from Earth, a moon of Saturn, Titan, that is eerily Earth-like. You look at these pictures, you look at pictures of lakes, of clouds, of river deltas, hydrological cycle, and it looks like an Earth-like planet, but it's not Earth-like. It's bizarre and different. It has an atmosphere that's made of the same stuff you're breathing and is as thick as the air you're breathing. Nitrogen, and actually the pressure twice that of the surface of the Earth. But Titan is a cold place, so this cannot be water. All the evidence suggests that the lakes on Titan, that one on the left is as big as Lake Superior, so these are substantial bodies of liquid. All the evidence suggests it must be made of ethane and methane, with perhaps a little ammonia and water mixed in. So if life exists on Europa, and we simply don't know if it's possible, it would have a distinct biological basis. It would be a completely different version of biology, making it very exciting. Nobody knows if that's possible. We've only landed on Europa once by the Huygens lander 10 years ago. It took a half an hour of data before the batteries died. So we'd love to go back and learn more about that. These are the compelling targets in the outer solar system for people who want to look for life nearby, in our backyard. And surprises too. Found pretty much by accident, geysers, icy geysers, jets of tiny ice particles erupting from a subsurface ocean in Enceladus, another moon of Saturn, and going out into space. There are 50 objects in the solar system bigger. It's the size of Rhode Island. Nobody, until this discovery, had any hint of a thought that Enceladus might have all the ingredients for life, but it does. And so it seems that in the solar system alone, with Earth being the watery planet that's in the Goldilocks zone where the temperature is just right for water to be on the surface, there are an additional 12, maybe 15 worlds, moons of giant planets typically, much further from the sun, that have all the ingredients for life, by which I mean water, a local energy source, and carbon-rich material. So that's very exciting. The solar system is by no means dead. Mars could have life right now under the surface, and some of these icy moons could host microbial life under their surfaces. It's extremely hard to do this research. As you know, there's a rover on Mars right now, the Curiosity rover, the size of an SUV. It's a pretty impressive machine. It was never built to detect life, and that's not really what it's doing. And if this water exists, it's likely to be tens of meters down. We have no drilling rig that can get that deep. That will need a whole new generation of Mars rovers, or perhaps a base on Mars from which to do the research. So this is hard work, and it's going to take decades to get the answer. Meanwhile, in the realm of exoplanets, or planets around other stars, the progress has been literally breathtaking. From my perspective, I'm in the field, or on the edge of the field, and it's amazing to me. So we're in a situation now that was unimaginable a few decades ago, where we can take a familiar constellation in the southern sky and inspect by a special technique, or a pair of special techniques, in this case the 55th brightest star in this constellation, barely visible to the naked eye, a rather undistinguished star. And in this case, with the telescope, of course, we can do through the solar system, the warp speed, it's 110 light years away, and learn that this star, this sun-like star, is surrounded, in this case, by 4 gas giant planets. We can learn their orbits, their sizes, their masses. We can't tell if there's life on them or diagnose them in detail, but it's a lot of information. And this is just one solar system. There are a couple of solar systems that have been found with 7, 8, even 9 planets, making them more abundant than our solar system. So these are rich planetary systems whose existence was unknown only 20 years ago. The method by which we learn this information is an indirect method. These planets are too faint to see. So what happens is the planet tugs the star that it orbits, and you see the wobble, and we measure that with a Doppler shift, and then if the planet orbits in the plane in the equatorial plane, as you see, it will pass in front of the star and dim it slightly each orbit. So those two techniques are how all of these planets have been found. And summarizing the progress in just 20 years is one diagram here where you see the discovery of planets, their mass is vertical axis, their date of discovery. 1995, 51 Impey, a discovery that will virtually certainly lead to a Nobel Prize to a pair of Swiss researchers who used a very small telescope, less than 1 meter in size, to find this planet. But look at the march of progress. The first planet of Earth mass was found just a couple of years ago. And this steady march of a factor of 1,000 gain in the lowest mass planet we can detect is actually exponential progress. It's logarithmic. It's very unusual in science, outside of information technology, to see this kind of progress, dramatic. You can still see, however, that most of the planets being found are more like Jupiter and Neptune. They're gas giants. So the rocky terrestrial planets, the ones we might be interested in for life, are still the more extreme planets, the more difficult to find, and they're in the minority. We've known for a long time that we expect these planets to exist. This is a simulation of how astronomers imagine planets form. At the bottom, you see planetesimals, or rocky chunks that are small to asteroid size, and you start with thousands of them orbiting in a disk, colliding together, sticking by gravity, and as you watch this simulation with the time ticking inside a computer, you can see the gradual formation by accretion, gravitational sticking together of these rocks, into some terrestrial planets. And 1 AU is the distance of the Earth from the Sun, 1.5 the distance of the Mars from the Sun. So in these hypothetical computed solar systems, we form a set of rocky planets. One that's roughly Earth-like, one that's even Mars-like and Venus-like. That's a coincidence. You can run the simulation many, many times and harvest the planets that come out. So we've seen this, that in every case, when we put a simulation together of how a solar system might form from simple ingredients, from just a cloud of gas and dust, you do form rocky planets. So it shouldn't surprise us that they exist and are there to be found. Notice the whole process is fairly rapid. It takes about 100 million years. And this in a situation where our solar system is 4.5 billion years old. So it doesn't take long. You can do more than that. In the simulations, you can put the chemical and geological ingredients in the simulation and follow those as well. And so in one set of these simulations, the water was followed. The mantra of NASA, as it looks for life in the solar system, is follow the water, because we think life needs water. And in these simulations of planets forming, you can follow the water too. And once again, in the Copernican sense, is our planet special? The answer is no. As a water world, it is not special, because in these simulations, you can see that there are not just many that are Earth-like in their water content of oceans, but there are many that have 10 to 100 times more water than the Earth does. So if life needs water, water is abundant. I'll just remind you briefly that carbon is one of the most abundant elements in the universe. It's formed all the way back to close to the Big Bang. We see it in the spectra of distant galaxies across time. And water is one of the most abundant molecules. So those ingredients of life, carbon and water, are not special to our solar system or any cosmic location. They are everywhere. The table has been set for life by the Big Bang, by stars generating carbon in their cores and injecting it into space. So we should not be surprised that there are habitable planets, but until a few years ago, putting a number on it was still speculation. What transformed that situation was the second of the techniques I described, where when the orbit of the solar system is aligned in the equatorial plane, you can see the planet cross in front of its star, and it makes a momentary dip in the brightness of the star. In this case, something like a Jupiter is passing something like the Sun, and Jupiter is 10 times smaller than the Sun, so the dip goes as the square, it's 1%. Earth is 10 times smaller than Jupiter, so that dip would only be 1/100%. Now that's hard, but it's doable from space. And so this eclipse or transit method has yielded phenomenal success in the search for planets in the last 5 years. And here's the summary of how that's gone. These are planets discovered by the Kepler satellite, the Kepler mission, which recently entered the sort of end of its useful scientific lifetime, but had 4 to 5 core years of productivity, is a 1-meter telescope in space. If you made a list of the world's largest telescopes, it doesn't crack the top 100. Not that impressive in size. But it was brilliantly designed to do one thing, and that one thing is to stare at one piece of sky, where there are 150,000 random stars, and stare at those stars and take data every 6 minutes for 5 years, looking for that momentary dip that you saw from a planet crossing the face of a star. And only some fraction of those stars will show that, but from the data, Kepler can develop a technique to understand what the true incidence of planets is. And the success is phenomenal. Just last year, Kepler had one press conference where they released almost 800 new planets. But remember, before 1995, 0 planets were known, and people had been looking for decades. So to have one data release of 800 new ones is pretty amazing progress. And here's a montage of some of the Kepler planets. And this is exactly how they're detected. The stars are not all the same size. Some are sun-like, some are bigger, some are smaller. But they all have a situation where the planets cross the face of the star. And when you watch for that to recur, you've measured the orbital period of the planet, and you know its distance from the star, and so you can decide whether it's habitable or not. You know how much energy comes from the star, the distance of the planet tells you whether liquid water could exist on that planet. So you have all the information you need to determine habitability. You also have situations where more than one planet orbits a single star. That's seen quite often. And since we have to put all this together, in astronomy it's called an R-rate, where you plot the orbits. Here's a sense of some of the Kepler orbits, not all of them. It's impossible to show all of them in one graph. And we'll zoom in on some of the more bizarre systems, because they're not Earth-like at all. Kepler was finding planets that whiz around their stars in less than a week. Remember, Mercury, the closest planet to the Sun, takes 3 months to go around the Sun. So a planet that orbits in less than a week is really whipping around. But let's cut to the chase. What about finding planets like ours, as close to ours as is possible to find? How it succeeded that Kepler has done phenomenally well in finding Earth-like planets. It only increased the inventory of Jupiters and Neptunes and big gas giants by a modest amount. It found a lot of what are called super-Earths, that are planets that are maybe between 2 and 4 times the mass of the Earth. And then it found a lot of Earths and increased those numbers by a substantial fraction. You can read off the graph. We now know of about 150 Earth-like planets. So this is amazing success. Also notice that in our solar system, there are no super-Earths. In the inner solar system, we have the Earth, Venus, which is almost a twin, and then Mars, which is much smaller, and Mercury, which is much smaller. So our solar system has no super-Earths. Out there in the universe, they exist, and they also can be habitable. And in the final inventory, the last data point is not yet in place because the team of this telescope, the science team, are working very hard on it. It's like it's the capstone, if you like, of their project. Here you can see the incidence, which is the fraction of all stars that have a planet of a particular character, divided in boxes into the size of the planet compared to Earth and the orbital period. And so you can see most of the Kepler planets are a little bigger than the Earth and moving much faster or closer to their stars, and therefore not habitable. And the final box, the one that would have Earth clones in it, is of course sitting there at 365 days, our orbital time. And that number is not yet known. But you don't have to know the number to see from the other numbers that it's going to be something like 5%. 1 in 20 of all stars is going to have an exactly Earth-like situation. And if you add together the numbers on that horizontal line, you can see that 1 in 5 or 1 in 4 stars have an Earth-like sized planet on some sort of an orbit. And if you add up all the numbers, you can see that essentially every star has a planet that's something like the Earth, or up to 6 or 8 times more massive. They are ubiquitous, they are everywhere. It's not like looking for a needle in a haystack. And we can drill down, take the best data from this mission and from other ground-based observations, and try and ask about the habitability of the planets involved. And so this graph pulls together the most habitable and most interesting of these planets, and then it does an interesting thing by calculating the habitability of the planets in our solar system on the right. Jupiter and Neptune, not habitable, not surprisingly, but the interesting one, and Earth is one, so it defines perfectly habitable. On some hot summer days in Tucson, it doesn't really feel like a habitable planet, but, well, and then if you've looked on the East Coast this year in winter, it certainly doesn't feel habitable. Let's just imagine Earth is perfect Eden, and we define it as one. You'll see that there are planets already in the books that are substantially more habitable than Mars by this index. And we think Mars could easily host microbial life. We would expect that it must or might under the surface. So that's very exciting. The other thing we realize in this work is that because of these habitable spots in the outer solar system that I mentioned, like Titan and Europa and Enceladus and other moons of the giant planets, that the habitable real estate is dominated by outer solar system situations, not by the Goldilocks place of the Earth at just so distance from the sun. And so this so-called cryogenic biosphere is bigger than the terrestrial biosphere, and we think that will be true elsewhere in the Milky Way as well. We also bring in the fact that most stars are not sun-like stars. Most stars are red or cool dwarfs. They are, to be habitable, their planets will have to snug closer to the star. So our sun is a nice healthy campfire, and the M dwarf, the cool dwarf, is a kind of feeble campfire. Well, if you huddle close enough to the feeble campfire, you get as much heat as from the bigger campfire of the Earth. So there is habitability around lower mass stars, and there are hundreds of times more of them. So that's an important point too. And when people question the cost of NASA missions, and I admit that some of the things that I do, that we do, are expensive, I make this particular comparison. So for $400 million, I admit it's not chump change, it's a lot of money, you can have a really cool movie by a famous director, James Cameron, about life on an exoplanetary system, or you can do the experiment, send the mission, they cost the same. And in one, you had a nice movie and you went home and talked about it. In the other, you got the answer, you advanced knowledge, you made a discovery. So Kepler has done this, and it's all happened very recently. Have we found an exact clone of the Earth? No. And we wouldn't expect to. And it's not necessary to if we're really only interested in the range of life, because life is robust on the Earth and lives in some pretty inhospitable places. So Earth 2.0, the closest we can find to a clone, won't be exactly like Earth 1.0. And the other thing, which is good or bad news depending on how you view it, is that the nearest Earth statistically is not likely to be right on our doorstep. It's likely to be 20, 30, maybe even 50 light years away. Now that's not close enough to go to anytime soon. So unfortunately, finding another home does not obviate us from the need to take care of Earth 1.0. We're never going to go to these planets. If we're lucky, we can learn about them with telescopes. So what are the implications of this research? All the numbers that I'm going to give you are lower numbers, lower bounds, because Kepler and these telescope observations have really only been looking for the planets. Earth-like planets in Earth-like situations. From the solar system as our example, we know that there are a dozen or more habitable spots in the outer solar system, and those are like the exomoons, like James Cameron's idea, Avatar. We have never detected an exomoon. The technique is not available yet that can find a moon of a giant planet in another solar system. It's too hard. So that remains to be discovered. We simply don't have those yet. And it may be 10 times more than the number of habitable Earths. There's also a category called nomads. When we make those simulations of how solar systems form, like the one I showed you where the Earth is building up in stages from rocks coming together, in all those simulations, planets, some subset of the planets that form are ejected. The early phases are unstable, the orbits haven't become regular, and so planets are ejected early on. And in most of these simulations, the number of, as they're called, nomads, that is, planets that got ejected from their star system and have no star nearby, can exceed or match the number of regular planets. And they're undetectable. They have no nearby star to tug, no nearby star to cross in front of. They're invisible, they're dark, they're far away. And so there are nomads that could be habitable, carry their own ecosystem with them, and we have no way of detecting them, but we speculate they exist. So the universe is a phenomenally diverse and abundant place, and we just do what we can do with these techniques. But let's put numbers on it and make at least a little analogy that could bring these home to what it means. Roughly 300 Earths or super-Earths discovered since 1995. Let's imagine them as grains of sand, each a little world that we'd love to know more about. Most in the immediate neighborhood of the sun, by which I mean within 100 or 200 light years. The projection in the Milky Way is of 10 billion habitable worlds in the Milky Way, and that's pretty much the number of sand grains in that sand pit. And then multiply by that order of magnitude for the habitable spots, the exomoons, and that's 100 billion habitable spots with all the ingredients for life. So just while you're absorbing numbers, just take a minute and digest that number. That is 100 billion petri dishes, potential biological experiments. And you could choose to tell me or speculate that they're all dead. Nothing happened on any of them. And I couldn't argue that because we don't know. But most astronomers are guessing that something has happened on some subset of them. And think about it, even if only 1 in a million of those habitable worlds like the Earth got life on them, essentially meaning that life is a fluke, you still have thousands of Earth-like planets with biology on them, thousands. So you can see why people get excited about learning more about those worlds. So we can't do it. We can't go there. We can't make images like this. It's dreaming about other worlds. We have to use our imaginations. So in this little montage, we'll visit maybe a dozen. We'll take a minute to do it. And some of them are arid and volcanic and nasty places. Some may have water. Some may be temperate, habitable. We don't know. So that little travelogue is a little hint of what's out there. And if we were to do this, if we wanted to do this for the 10 billion in the Milky Way, we would watch this at this rate for 100 years. Gives you a sense of what's out there. So astronomers pull all this together in terms of not just the number of habitable planets, but the possibility of companionship in the universe, or kinship. Intelligent life. That's the thing that will get our pulses going. Maybe microbes, maybe bacteria won't be interesting to most people. But intelligent life, sentient creatures, that will be interesting. It's called the Drake equation. It starts with the number of stars in the Milky Way, 400 billion. It takes the fraction of those that have planets, a number we now know, and then it takes the fraction that are habitable, a number we now know by projection. That's 20 billion. That's the raw material for going further. And then we have to speculate, because we do not know what fraction of those 20 billion actually end up with biology. I said it could be as low as 1 in a million. Some people think it's a lot more. They noticed that life started on Earth very, very early. Life was on Earth possibly within 500 million years of formation, when the Earth was a very nasty place. So, and all the ingredients are available in space and in the raw planet itself. So arguments can be made that it's quite likely to happen, but no fluke was involved. Being optimistic in that regard, that maybe 10 billion biological experiments got underway in our galaxy. Then it's very uncertain. I'll just say 1 in 100 end up producing intelligent life. So that's 10 billion microbial worlds and maybe 100 million worlds with large creatures. It happened on Earth. It's clearly not an unnatural thing. Evolution, it's now been demonstrated actually in an article, research article in Science just a week ago. There's a biological imperative that does lead to larger and more complex creatures. So it's not a fluke. But we don't know how often it happens. And then the last stage, what fraction of those intelligent creatures can get technology, travel through space, communicate, have telescopes? That could be anything. If it's 1 in 100, that's still 1 million civilizations, communicable, intelligent civilizations. Or maybe we're unique. Simply can't say. But this logic, this compelling large number logic, led the physicist Enrico Fermi in 1950, very early to speculate this kind of thing, to pose a question that attaches to his name: where are they? And what he did essentially was combine the fact that we're very young in our ability to travel in space or to do astronomy with telescopes, to know that a modest extrapolation of our current capability will let us travel to the stars. Maybe not ourselves, but with nanobots or at least with remote sensing. And also, he did know even then that there are likely to be many sites where this could have happened, and a lot of time for it to have happened. And so, his question became not are we alone, but where are they? There are so many of these places where this should happen or could have happened. And now that's becoming an interesting question, now that we have meat on the bones of these arguments by knowing how many habitable worlds there are. Of course, you have to be careful what you wish for, because while we think of ourselves with some elevated status in the universe, we ignore the Copernican principle of mediocrity here, because we still have a pretty good self-opinion. The aliens might think of us in a slightly different way, especially if they're a lot more advanced than us, which is statistically the most likely outcome. Since we've only just developed the ability to leave the planet, or sense other planets, or communicate with those sentient civilizations we think might exist, then statistically the most likely pen pals are going to be more advanced than us, perhaps a lot more advanced. And that may be something we don't want to know the answer to. So that's the status in our galaxy, and now in the last part of the talk I'm going to play it out onto the big arena of the universe. That's sort of my field, cosmology. Because I did pose a question at the beginning of the talk: how many habitable worlds are there? And I partially answered that question by saying, and this is just a number you can lodge away, it's one of those facts that you can, spend a little too much time in a supermarket checkout when you're speaking to your neighbor or stranger, just toss out there, oh, by the way, did you know that there are 20 billion habitable worlds in the Milky Way? And that'll get a nice conversation going. So that's a factoid you can lodge away. But that's just one galaxy. We're being very myopic and parochial by only talking about one galaxy, especially to me, who works on extragalactic stuff. So let's go out there and put the numbers together for the bigger universe. And of course, we're leveraging the work of Edwin Hubble, who did his pioneering work, the discovery of our galaxy, its size, the expansion of the universe, and the nature of other galaxies just up there, Mount Wilson, in the early part of the last century, almost 100 years ago. And of course, his work was a continuation of the Copernican idea, essentially telling us that we're not just mediocre in our planet and our star, but we're mediocre in our galaxy. in a very large and old universe. So he was the first to gain that awareness, and now we know a lot more. We've had 100 more years of telescopes to look at this. So we're small, the universe is large. Okay, we got that. How much larger? We can start with the facilities that let us count galaxies and determine essentially the stellar content of the entire universe. And you can see that at the moment, we're not only going out in space, we're going back in time, because it takes light a time to travel through the universe. So we're now looking at galaxies not only far away, but back in time. The Hubble Space Telescope takes us almost to the dawn of time, and the James Webb, which will launch in a year, will take us even closer. We're essentially looking back through 95% of the age of the universe to almost the entire stellar content. So the agenda of cosmology to count all the galaxies in the universe is done. Astronomers have actually done that in the last decade. So there's no uncertainty about that. And so I can put a reliable number on how many galaxies there are. Here is the deepest image of the sky ever made by the Hubble Space Telescope. This is a piece of sky that is smaller than the head of a pin held at arm's length. It's a tiny piece of the sky. And if you could count to the limit of the image, there are 3,000 galaxies. Each fuzzy smudge, none of these are stars, individual stars in our galaxy. Each is a distant stellar system, mostly a few billion light years away. It's a phenomenal inventory just in that tiny patch of sky. Here is just zooming in on a very small piece of it and panning across so you can see a little more in detail that these are real galaxies like the Milky Way with spiral arms and some other galaxies like ellipticals. And when we look at this, it's impossible not to imagine, knowing that there are 20 billion habitable worlds in that galaxy that's just disappearing, it's impossible not to imagine that someone or something is not looking back at us with a telescope from any or all of these galaxies. So let's put that number together. Conservatively, because I've been conservative in talking about habitable zones, there are 1,000 billion, 10 to the power 21, 21 zeros, terrestrial planets in the universe, Earth-like planets that are fully capable of supporting life. And there's a real estate of time as well as space. Many of these Earth-like planets could have formed billions of years, up to about 8 billion years before the Earth formed. That should make you think too, because if you're talking about a mismatch in evolution, imagine a life form that had a 4, 5, 8 billion year head start on ours. That's almost unimaginable, because you go back a billion years on the Earth and there's nothing that you could see with your eye. All life is microscopic. So we've come a long way in Earth evolution in just a few 100 million years. What does that 1,000 billion number mean? I gave you the sandpit for the galaxy. For the entire visible universe, we're talking not about all the grains of sand on this whole beach off into the distance. Pretty close to, various people have done this calculation online, and we have students do it as part of an exercise. It's pretty close to the number of grains of sand on all the beaches of the Earth. So now let that sink in a little bit. Imagine a wonderful holiday for a year. You take a sabbatical, or you just take a year off school and you just go around all the beaches of the Earth. What a nice thing to do. You know, make sure you get that summer, winter, northern, southern hemisphere thing right. And then you're just tracking across these beaches, and each of those grains of sand that you can see off to the horizon on all these beaches, if you could even do it in a year, is a world. It's a biological potential experiment. So that's a pretty amazing number. But the epistemological question, is there life in the universe or are we alone, has to be posited in terms of this number, this big number. And who's to say that civilizations of sufficient technological prowess couldn't communicate across a galaxy or between galaxies? Who's to say? Just because we're infants in our space capability or our technology, we're just babies at this. So let's keep following this flow, because I'm not done yet, but I'm getting close to done. This is the diagram that Hubble made all those years ago, and it's gone a lot further since Hubble's time. Hubble's data was confined to that tiny little blue box. sitting right down near the origin, because he tracked the velocity or the expansion speed of galaxies, of the universe itself, versus the distance of those galaxies in millions of light years. So his original data was nearby universe. We followed Hubble's law, as it's called, all the way out to a situation where if you know what the velocity of light is, we're actually finding galaxies that are in the distant past, that are moving away from us as we observe them at close to the speed of light. And the implication of that is quite interesting in the Big Bang model. That's what the expansion is caused by in cosmology. So it's getting a little esoteric, but I hope you can follow this thought process, that light travels very simply and directly in the local universe, 300,000 kilometers per second from A to B, from the Earth to the Moon, in the lab, wherever we measure it. But the universe itself, as it expands, is governed by general relativity. And if you dig into the math of general relativity, there's no speed limit there. It is not violating a law of nature in general relativity, our best theory of gravity, from Einstein, to say that the universe expands faster than light. It's perfectly okay within the theory. And in the Big Bang model, the universe did expand faster than light early on. And so you have this bizarre situation, which is attempted to convey with this diagram below, where galaxies in the early universe are actually receding from each other faster than light. So light cannot transmit between the galaxies. As the universe slows down in its expansion rate over time, the light eventually can reach you from a more distant galaxy. That has a very important implication in cosmology. If the universe was once expanding faster than light, and we can show that, and we can, then it means there are regions of space and time, there are regions of space that we've not yet seen, because they were dragged beyond our view with any telescope by the superfast expansion. And that means that the 100 billion galaxy number I use to calculate habitable worlds is a lower limit. That's just the observable universe. And if you ask in the theory of cosmology, how much bigger could the space-time we can see be than the space-time we can see with our telescopes, the answer varies, but it's probably factors of hundreds or thousands. So now you can bump up that number I gave you, like 1,000 billion billion, by another factor of 100 or 1,000 for all those pieces of the universe we can't yet see. If we're patient enough, we'll eventually see them. Eventually the light will reach us. But the universe is only 14 billion years old. It does not have time for those very distant places to communicate with us. And there's one more twist to this story. So if you're keeping track, we're now up to 10 to the 21 times maybe another 1,000, so 10 to the 24 habitable worlds. Maybe that's enough for you. Maybe you're just happy and you should say, I should just stop. But you know, there's a compulsion, there's a twitch, there's a itch in astronomy that has to be itched, scratched, and I'm going to just go there right now. Because in cosmology, there's one final ingredient, a secret sauce. We have to, and this is a little esoteric, so I'm going to glide over all the technical details. There's a hypothetical phase of the early universe when it went through what's called inflation. And it's represented really schematically by this very rapid widening or increase in size of the universe. And that inflation, as it's called, where the universe essentially went from a very tiny microscopic size to a macroscopic size in a tiny, tiny, tiny fraction of a second, it's required to explain why the universe is overall uniform, especially the radiation left over from the Big Bang. It's smooth to about 1 part in 10 to the 5, 100,000. And that is very hard to explain unless you posit inflation. So I'm just going to mention inflation as an ingredient by which we need, it's an ingredient we need to understand the Big Bang radiation especially, which is brilliant evidence for a hot early universe, but needs this extra component to be understandable. Following that thought leads to an idea called multiverse. This is my last topic that I'll leave you with. Now we venture into, so we're definitely going out on the limb here. We're now, now I'm definitely going to just try and blow your minds. I'm not even going to be embarrassed about that. So in the Big Bang, we're in a situation where the very small and very large are unified. Virtually, and this is symbolized in this diagram by an Ouroboros, which is the snake eating its tail. This is an ancient mythic symbol from many world cultures, and it's been co-opted by physics and astronomy to symbolize the fact that our understanding of the fundamental nature of matter, that is what particles are made of, may only come from studying of the intense energy and temperature of the Big Bang itself. Because diagnosing the nature of matter, the fundamental nature of nature, if you like, can only happen with phenomenal energy at our disposal, more than is available in any lab or accelerator. For instance, this is how well we can do with accelerators. So I'm plotting temperature on a crazy scale that goes up to 10 to the power 32 Kelvin. And time since the Big Bang. The relationship between the temperature of the universe and time is very simple in this relationship. It's a power law. The highest temperature you can make with a Large Hadron Collider, the biggest accelerator we have, the discoverer of the Higgs particle just a few years ago, corresponds to about 100 trillionth of a second after the Big Bang. So we have used lab physics, terrestrial physics, in these huge accelerators to diagnose physical conditions corresponding to about 1,000 trillion Kelvin, an amazing temperature, and you can only reach it for 20 fractions of a second. And that corresponds to a very, very tiny instant after the Big Bang. What we've learned from these physics experiments is that the four forces of nature, and then I'm showing the same axis here, temperature, going from cold on the left to super, super crazy hot on the right. And here I'm showing strength of the forces of nature. In the old cold universe on the left-hand edge, the four forces of nature, gravity, by far the weakest, electromagnetism, responsible for light, and the weak and strong force inside the atomic nucleus are very different in strengths, and we actually don't really understand why. But physics has told us, and high energy physics has told us, that if you increase the temperature, we'll go back in time towards the Big Bang, these forces start to merge. And we still have the first of those mergers, electromagnetism and the weak force, at CERN in the 1970s, and about 4 or 5 Nobel Prizes were awarded for that. It was a huge discovery in physics. The speculation of inflation is that inflation was triggered by the subsequent merger of the strong force with the electroweak force. That was the trigger to this super fast expansion of the universe. So now I've just given you two ingredients. I've given you the idea in the Big Bang that to explain the radiation left over from it, we need a super fast early expansion phase from microscopic size to something you can see. And we've got the idea from physics that when forces of nature diverge as the universe cools, you have a mechanism that could trigger this rapid expansion. So you have a physical mechanism and you have a need for something like that from cosmology. And now people run with it. And this is what it would look like. In the history of the universe, where now is on the right-hand side and the Big Bang is on the left side, you can see that the universe inflated from 10 to the minus 35 meters, you can imagine that, to about 10 centimeters, about grapefruit size. It's always reassuring to me that to think of the universe as like a grapefruit, that's fine, I can understand a grapefruit. What this inflation must have done is it must have taken quantum level fluctuations of space-time and blown them up to large size, to macroscopic, room-sized, grapefruit-sized entities, galaxy-sized entities even. And so, in the last 2 minutes of my talk, we venture into the crazy world of string theory, the frontiers of physics, the limits of knowledge of everything, space and time and matter and so on. So, if inflation happened, as cosmologists think it must have to explain the universe we live in, and if the trigger for inflation was a deunification, if you like, of some of the forces of nature, then these speckles, which you're now looking at microwaves left over from the Big Bang, and the difference between the bluest blue spot and the reddest red spot is just that 1 part in 100,000 of temperature. Tiny, tiny variation in temperature, but those little speckles were the seeds that would one day grow galaxies, and of course stars and planets and people. So without that, if it were perfectly smooth, we wouldn't be here talking about it. There were these fluctuations, and in the theory of inflation, these fluctuations are quantum fluctuations. It's saying quite literally that our galaxy and all the others, each of which has 20 billion habitable worlds, was once a quantum fluctuation. It's a crazy, amazing idea. and we don't know if it's totally correct. But if that's the case, then you have a mechanism for multiple realizations of the universe, because we all know quantum fluctuations come and go, and they're randomly different, that the quantum world is kind of crazy that way. So the people who work on string theory have tried to put numbers on this, and they've actually realized that the substrate state of the universe at the Big Bang, if you could just take it to the Big Bang itself, you have a situation where the vacuum of space, because there was nothing there yet, it was just vacuum, could have 10 to the power 500 possible energy states. And some of those energy states could inflate into universes, some might not inflate, some might be stillborn. And this is the multiverse idea. That if one quantum fluctuation could have blown up into our observable universe, there could have been others that did other things. We just don't know where they are, we don't know much to say about them. And in a bizarre response to Fermi, when he's saying, where are they? Because we haven't seen them, let's be honest, we haven't seen the intelligent aliens, they're not at our doorstep, they're not talking to us all the time with radio waves or pulsars or lasers. Then in that response to Fermi, most of the universes in the multiverse are inhospitable to life, and we just happen to live in the Goldilocks universe, in this multiverse ensemble. And then if that were the case, we would be alone. Can't really answer the question that way, but that's the speculation. So to kill you completely with the big numbers, here are my final set of big numbers. In generic inflation, that's just vanilla inflation, the way they calculate it, the number of distinguishable universes, 10 to the power 10 to the power 16. That's a double exponent, so don't, circuits will start melting up here if you can see what that means. I've taken you up to 10 to the 24 habitable worlds. That's totally straight back inside ultra-conservative vanilla number for habitable worlds. You can put that in the bank. This one, I wouldn't put it in the bank. I mean, I don't know how you put something in the bank that big anyway. The edge of the observable universe, that is our universe, 100 billion galaxies, is 10 to the 27 meters. But in a situation where there are all these multiverse situations, you can actually calculate the probability that you will find, for instance, you know how many atoms you have. I mean, everyone should know that, but if you knew how many atoms you have, you could work out how far away you'd have to go in the multiverse to find an exact copy of you. Statistically, it's got to happen. And there's the number, 10 to the 29 meters in the multiverse. Now that's far enough that you're not going to bump into your doppelganger in the shopping mall or something. They're quite a long way away. You can even, because the numbers are so prodigious, you can even calculate how far away you go in the multiverse before you find a complete identical copy of your entire universe with 100 billion galaxies and 1,000 billion habitable worlds. A complete identical copy in the multiverse. And I thought this was where I should stop until I ran across a paper in a peer-reviewed journal in physics, supposedly a reputable journal, which talked about a variant of inflation called eternal inflation, which actually samples all the possible laws of physics. And in that theory, the number of possible distinguishable universes is 10 to the power 10 to the power 10 million. And that's the largest number I've ever seen, and I've been around a while, and I read these kind of whacked out journals on theoretical physics when I can. So that's the biggest number I've seen. And I'm not even going to go to the place of wondering how much life there is in that many universes, or what it's like. So we have these scenarios, and then also these scenarios I'll just mention briefly to finish, that these are scenarios where you finesse the Big Bang. In the multiverse scenario, the Big Bang is just an occurrence in a continuum of space-time where essentially time does not exist. And so the Big Bang is an origination event for everything is meaningless because the multiverses exist in a timeless domain. And so it's an eternal process as well. We've made sort of space endless and time eternal. And whether or not that last part that I told you about is right, I think it's amazing that we're made of these tiny particles and we're part of a vast universe, whether it's a multiverse vast or just 100 billion galaxy vast, it's pretty big. And yet somehow we can keep them both in our head. So to bring you down briefly from such a giddy place with high numbers, I'll leave you with the sky. Thank you.